contrary to previous couple of presentations, which really involved a lot of knowledge, continuum mechanics in general, thermodynamics, and all these conservation integrals. But here I want to present you something completely different. So, as the introduction, let me say that this risk-based approach that I will show is based on risk matrix. This is a simple matrix. If we know probability or something like that, if we know consequence, which I explain a bit in more detail soon, then we can have a plot of these two values. And in these 25 matrix spaces, we go from low risk to extreme risk, depending on these values. 5 times 5 is usual way of doing it, but it can be 3 by 3 or 7 by 7 or whatever you think it should be. In any case, risk is here product of probability and the consequence. That's also important. For example, in the aeronautical industry for commercial airplanes, consequence is catastrophe. Fortunately, probability is 10 to -7, I think, in these days. Now, risk matrix, once again, a couple of more details about consequences. They are categorized according to what would be with health, safety, environment, business, and security. So if all of these are affected, we'll probably have the highest category for consequence. And if not, then it would be one of the lower consequence categories. And that is shown here in more details. For people, property, environment, and reputation, you can go all the way. And this is also provisional. You can have different values, different criteria, but basically, if somebody gets killed, then it should be can get killed. That is category 5 or category E, which is the worst. So for the consequences, that was it. Now to see about probability and how we connect with the structural integrity. That's the major issue here. So you can see here that probability is a bit replaced with the term likelihood, because we will deal more with likelihood. Probability is mathematical term, and mathematicians would object to using it here. So likelihood here in the static case is calculated by using failure assessment diagram. Here we have on the ordinate the ratio between stress intensity factor and its critical value. On the axis, we have the ratio of net stress in the area of defect, crack-like defect, and once again, critical stress, whatever it is. So those are simple values, linear elasticity, simple values, but it combines, it also concerns the eventual plastic collapse, because if net stress reaches critical stress, then we go into plasticity. And this is the limit curve. So if the point that you calculate is here, it is safe. Of course, if you did it conservative way. Outside this limit, it is not safe, not necessarily that it will fail, but you don't count on its safety. And then, since in this point, likelihood is 0, and in this point, likelihood is 1, because we reached limit state, any point in between is just a ratio between this and that. So very simple reasoning. If stress is 0, then likelihood is 0. If stress is such that we are at the limit line, then likelihood is 1. And since this is linear elastic analysis, everything in between is just the ratio. In the case of fatigue, it is maybe even simpler, because if we know crack length versus number of cycles, and we know that for simple cases, even analytically using directly Paris law, of course, under condition that we know C and M, then we have graphs like this. And then let's say after 1,000,000 cycles, likelihood of failure is just slightly below 0.5, because you can see that at 2,030,000 cycles, this will fail. So simple engineering tool. Imagine a situation, especially for this static case, that somebody from hydro power plant is calling you, and that was the real situation, saying that at the regular monitoring, they found unacceptable defect. And then they ask, can you help us to decide what to do to repair it, to stop the power plant, or to let it run if it is still safe? And then, of course, naturally, you would ask, okay, what is the deadline? And they would say, well, this afternoon. So in that case, and if the vessel is simple, we can do a lot by these methods that I'm showing here. So something similar is here presented as the case study. Not exactly that what I mentioned from real life, because this example has both static and fatigue analysis, and that one was only static. So here we have classical oil rig drilling casing pipe that really had crack-like defect, as shown here, but that was a part of research, really. So we even could do some strain. We could do fracture mechanics testing to get precise values for fracture toughness in the base metal, heat affected zone, and weld metal. Maybe you should open the door, because they are no, just joke, because they are discussing welded joints. And then we also were able in this research to measure strains. This is a long time ago. Nowadays, we would use digital image correlation or any other optical non-contact system. But good old strain gauges showed strains, sorry for this, strains versus pressure. And the working pressure was around 10. So we went up to 22. It even still didn't fail, but we went into nonlinear region to check simple analytical solutions, because for this, what I have shown, there are simple analytical solutions for the stress intensity factor, even though this is the surface crack, not through the thickness crack. But you can find it in this, well, once upon a time, this very thick handbook. Nowadays, internet, Google knows everything, just ask. So simple way, in this case, was to calculate K1, and I presented how we measured K1C, and then calculation of stress is even simpler, but net stress close to crack-like defect. And then we got a point here. So that point produced about 72% of probability, likelihood, better to say, and the consequence was estimated as 4, not the worst one, because there will be some environmental effect, but nobody would be killed. And in money terms, not a big deal. More it's about reputation of the company because of eventual oil spillage. But in any case, we are somewhere here, which is high risk. maybe even very high, but not extreme. But the point here is also, I will mention it at the end of the day, that our job as engineers, which we can do in 2 hours, I think, in this case, is to provide the management with such a risk matrix. They have to decide what to do, not we, or the owner or whoever. Okay, that simple way of doing things in this case was also possible to make for the fatigue, because these pipes really work under amplitude loading. Geometry is simple enough. Once you can find analytical solution for stress intensity factor, you don't need anything else. So you can take initial Clark defect as 3.5 milliliter in depth, or maybe suppose some other values just to check what would be the outcome. Then you may take 20 megapascals that was really operational value, or maybe, no, 21 was, so 20 was just slightly lower and 25 was just to see what was going on. And then we would get likelihood for fatigue failure as shown here. So for the real situation, it's just 0.14. For this one, it would fail. But anyhow, all of them are now also put into a risk matrix, and that provides simple engineering tool to present to the management. And as I said, then they decide. Now, of course, if you have not just 2 hours, but 2 days or a couple of days, you can also use finite element method, and then to get more precise stresses and fatigue crack growth. But if everything was done in the conservative way, and if we got, let's say, satisfying results from point of view of management so that they can run it further on, in conservative way, you don't need this. Anyhow, we did it because, as I told you, this was a part of research as well. So conclusions, I sorry, practically told you all of them. And I think everything is clear. Just let me emphasize this once again. Final decision is not on us. We can relax. They have to worry. I mean, managers and owners. And for that money that they earn, they should worry. Thank you.